All right, good afternoon, everybody. So we're going back to Calc 2. We're going to take a little break from improper integrals, and before we jump into Chapter 8, we're gonna finish off Chapter 7. Now, you guys can let me know if you want a test question on this. I don't particularly like to ask them so much because they're tedious, they're time-consuming, and they're also very easy. So, you know, it takes a long time, but at the same time, they're an easy question. I would not expect you to memorize the formulas that we're going to use today. I would, you know, in the before times, I would put them down on your sheet. I don't know if they have you do this or not, but if I do ask you a question like this, I will come up with a way to put these formulas down on the problem so that you can reference them, because quite frankly, they're numerical recipes. When you need them, you go look them up. Okay, that's really all there is to it. I'm not, you know, when you say use the trapezoid rule, like, you're not expected to memorize these things. Okay, every other time I've done it, written them down and just let you guys have at it. Okay, but like I said, they are tedious to do this, but I don't know what we want to do with that. Okay, so yeah, what we're doing here, okay, is we are approximating integrals with a numerical method. Okay, so here's the idea. Okay, now I'm just going to draw a little, you know, a random curve here, and the idea, right, excuse me, is that we are going to go ahead and subdivide these intervals. Okay, now here's the pros and the cons for this one. The more intervals you have, the more operations it's going to take to get you a proper area here. However, the more accurate you're going to be. Okay, so whatever these intervals are, okay, we'll say this is A and this is B. Okay, so we'll say that our delta x is equal to B minus A over the number of intervals. These are your two endpoints. Okay, these are your number of intervals. All right, and this technique, all of these techniques assume that you have equally sized intervals. They, you know, that's all there is to it. That's not required by the summation. You don't have to have each delta x be exactly the same size. But you know, so if you have a, you know, curve that looks something like this, and then something like that, there's no reason to subdivide all of these up. It's a rectangle. Okay, there's no reason to subdivide those up. It's a rectangle. So in this case, we do make equal things because that's, you know, it's an algorithm for a computer or for people to do by hand. So we want the fewest amount of thought available to have to sort this thing out. So there's one, you know, we learned one last year. Okay. I want to do one. We learned one type last year, and that was we could take the left side rectangle here and come up with these areas. Okay, and that's they're going to call that L. Okay, for the left side. You could also, right? You could also make this rectangle. One's going to overestimate, the other one's going to underestimate, and it actually depends on the concavity here, okay, about what you're going to be dealing with. You know, if you have a graph that looks something like this, you know, we want blue. On my graph, if I have a graph something like this, right? Well, clearly the left side, right, is going to overestimate. The right side is going to underestimate. But if you have a graph that, you know, something like that, then the left-hand side is, right, the left-hand side is going to underestimate. It's going to be the opposite, okay, because of the concavity. So it's something you have to be aware of. If you know, right, that's one of the things this is an important section but I really hate how it's presented to you because they pretend as if you actually have answers or you actually have functions, all right? And a lot of times you guys are going to go into industry, and by the way, if you're going to go into engineering and you can get any experience in a lab, please take that, because that's really invaluable lab experience for you. And it's once you get on a job, it's a lot harder to lose a position because you have lab experience. It's not hard to get promoted. People always need to run labs, okay? And it may not be exactly where you want to take your career, but it's a really good first step to doing that. So, I mean, I've survived. I haven't survived. I didn't survive the department cleansing because I'm not a lab guy. But the people who were lab guys did survive the cleansing. So I would encourage you, if you can get lab experience, you can. But most of the time, you're going to get a collection, right? You're gonna run an experiment. There's your function, okay? Like, which function is it? Like, I don't know, here's a bunch of dots. And maybe you have to figure out the energy of the system here, and you need to figure out the area under the curve. Best of luck. There's a lot of numerical methods you can do to get this, okay? There really are. I'm not saying best of luck, like, there's no way to do it and you're on your own. You take a class called Numerical Methods, you're going to learn a dozen and one ways of how to connect the dots, okay? But then you have to figure out the area underneath of them, and that's where your calculus comes in. So one way is to connect the dots, just to connect the dots like a fourth grader would, and then draw little rectangles underneath of it. That's fine, okay, it works. But better might be to take the midpoint here, right, and come up with, I really wish I could like copy and paste this thing. Let's use that color. Okay, so we can come up with a value here, right? And this is going to be a little bit of both, right? It's going to be over and under. So the way you figure that out is you figure out, well, is the left-hand side over or under, the right-hand side is over or under, the midpoint's going to be between them. Okay, that's how we're going to do that. So that's one way to figure out the area under the curve. Okay, you want to hear something really ingenious about that one. Way back in the day. Actually, no, I won't say back in the day because I think they still do it. The people who work in chemistry labs, they know the density of the paper that their plots are out on. So when they get a plot and they have to figure out the integral of that plot, they will cut it with scissors, right? That skill you learned in kindergarten, and then place it on a scale and then multiply by the density of the paper and get the area under the curve that way. So there's more than just this couple handful of ways of getting it. We have left and right. We have midpoint, which is, I'll tell you, these are tedious things because now you have to figure out, like, whatever x0 is and x1 is, you got to figure out what's in between them, and hopefully you have a dot there. Okay. Then there's some other methods that we could use. Okay, there's a method where, again, I'm going to draw my random function here. All right, what we could do, all right, is we could, instead of using little rectangles, we could go ahead and use a trapezoid. Right? Okay, I'm trying to draw this so that it's close but not perfect, because that's really what happens. All right. So we could do that. We can get a trapezoid. Okay, and that's called the Trapezoid Rule. Okay. So the Trapezoid Rule, that's nice. It's pretty accurate, and it doesn't have some of the restrictions that the next one does. I.e., if there's an odd number that you have, you can go ahead and use the Trapezoid Rule. It doesn't care. Okay, and then somebody figured out, like, hey, instead of using a trapezoid, if we put 3 points together, right? If I have any three particular points, we can figure out a parabola. And since parabola tends to have curved tops, this might be a better fit. So if we have, here's my here's my values. Okay, we might be able to fit a parabola to this. Oops, it'll go through all 3 points. Okay, again, it won't be perfect. Okay, so if I have a point here, this point, and this point, right, it'll probably, it might do something like that. Okay, but the idea is that these parabolas will actually approximate these functions even better than a trapezoid does, because they have a curved top, and that's going to even be better. So this one is not called the parabola rule. Okay, even though the last one is called the trapezoid rule, this one is called Simpson's rule. Okay. And I think in almost every case, Simpson's rule is a little bit more accurate than the trapezoid rule. Trapezoid rule might be slightly easier to calculate, although with spreadsheets, with programming these days, there really isn't much of a savings to go to the trapezoid rule. Okay, so almost all of the time, we use Simpson's rule for doing this stuff. Okay, oops, not Simpson's rule, it's just Simpson's rule. All right, and to this day, I remember doing a physics lab, and I cannot remember what lab it was, but this is what happened, was we got a whole bunch of dots, and they were like, okay, well, figure out the energy in the system, go ahead and integrate that. It's a bunch, and it was on the really, really flimsy paper. It's just a bunch of dots. I'm looking, like, at least it was graph paper, right? So we asked the lab TA, I'm like, how do you want us to do that? Like, you want us to count the blocks? They were tiny, tiny little blocks. Oh, it was terrible. I should have gone to the photocopier and blown that up so we could count the blocks better. But yeah, we dutifully counted all the little blocks. But really, what we should have done. So remember this for your engineering class when you have to do this. You're going to come off being the smartest person in the room. Everybody's going to want to be your partner because you're the smart person. But you can get these values because you can just read them off the chart, right? Make a list. And then what we're going to do is we're going to use Simpson's rule. And I would say the accuracy you're going to get from Simpson's rule is worth excluding. Like, if you have an odd one, I would just truncate it and get this one instead, right? Or truncate the first one and get that one. That's how good of the savings it is. But if you want to use trapezoid rule, that's okay too. See how close you get. Okay. So like again, I don't expect people to memorize these formulas. I would happily put them down on a piece of paper for you, or provide them in some way, okay, to do this. I'm not really going to go over the midpoint rule because honestly, where it is a nice approximation, it's not really a great approximation for you. Okay, so let's see, do we have a statement saying what the heck the trapezoid rule is? Right there. Okay, so I'm just going to write it down so we could do some problems with it and then kind of get an idea for the algorithm. Okay, so what we're going to say here, okay, is we have between a and b, right, because it's directed to definite integral, f of x. And again, you probably, the book paints this picture like you're always going to have an analytic form, that means a formula of f of x. But the reality is, like, you are not getting an analytic form of f of x, okay? And we're going to say that this is the trapezoid rule, and this is equal to the, so we're going to have delta x over 2, right? That's your spacing, right? That's the size of your spacing, which is b over a, right? This was b minus a over, in this case, 2n, because it's b over a over n, and then it's half of that, okay? And then we're just going to have this, and it's just going to be f of x0 plus twice f of x1 plus twice f of x2 plus dot dot dot. And then we end up with f of xn at the end. Okay, so the first one has a coefficient of 1. The last one has a coefficient of 1. Everything else has a coefficient of 2. All right. So we're going to go ahead and we're going to try some of this stuff out. Okay. And see what we can do. Okay, so I usually pick really easy problems to do this with because, again, These get real tedious real fast, and honestly, this is what we invented spreadsheets for. Okay, this is this kind of a problem where if you have a spreadsheet, you will do it as a spreadsheet. Okay, so that's the other joke is you know, your education experience and what you're going to be doing in, say, let's go between 1 and 5. All right, this is 1 over x, okay, and we'll say our delta x is equal to 1. So we're going to go from 1 to 2, 2 to 3, 3 to 4, and 4 to 5, right? So we have 1, 2, 3, 4 regions here. All right. And I'm just trying to show you this as a way of how do you do this, try to make it as least tedious as possible. Yeah. Like I said, it's a really important skill because in reality, when you're working, this is the function you get. All right. So we're going to practice with an easy one, and then we'll let you go with that. Okay. So we're just going to make a little table here. Okay. We have x, 1, 2, 3, 4, and 5. Okay, sorry, my youngest cat is vocal for some reason. I'm not really sure why. Oops, here we go. And here's my f of x, right? F of 1 is 1. F of 2, half. F of 3, a third. F of 4, and f of 5. Okay. And then what we're going to do is we're going to say, well, this is either delta x over 2 or b minus a over n over 2. Either way, because delta x is equal to b minus a over n. In this case, we would say, well, my b is 5, minus my a is 1. And then how many subdivisions do we have? We have 1, 2, 3, 4 subdivisions. Okay, so 5 minus 1 is 4 over 4 is equal to 1. And we already stated that delta x was equal to 1. Okay. I'm not sure if your book is going to use h or not, but if they do, that's what they mean is delta x. Okay. Amazing that they do it that way. Okay, so just going through the formula now. Okay, so just a little bit of practice to go through the formula. Again, you know, spreadsheets would help. Okay, but my t of n, right? My t of 4 here. Okay, because we're using 4 subdivisions. Okay, and I don't think you really need to put the little subscript there. But we're going to say, okay, well, that's going to be 1/2, or, right? Because delta x was 1, 1/2. And then we're going to have the first one, and then twice f of 2. And I'll tell you what, we'll set it up a little bit easier. Set this up a little bit smarter. So 1/2 f of 1 plus 2 f of 2 plus 2 f of 3 plus 2 f of 4. And then the last one plus f of 5. Right. And then we'll just go ahead and say, well, this is half. And then we have what? We have 1 plus 2 times a half plus 2 times a third plus 2 times a fourth plus a fifth. All right. And we just got to add this up. Okay, that now you see why we need a spreadsheet. So what is this? A half, and then we're going to have 1 plus 1 plus 2/3 plus a half plus a fifth. I'm going to cheat. I'm going to use the oracle. 1 plus, I should have just said 2 plus 2 over 3 plus half plus a fifth equals. And we got 3.36667 stuff. Okay. Go ahead, forgive me this. I just feel more comfortable with the fractions. Okay. 101 over 30. Okay. See, are we glad we live in the 21st century where you have access to stuff like this as opposed to, you know, 1970s, 1960s, where you would get to do this all on your own. Okay. So how close did we get? Oh, did I get this 1/2? I don't think I did. Okay, I don't think I put that 1/2 in. So this is 101/60. Okay. Okay. So what is, right? What is this? We know we could do this one, right? That is natural log of 5 minus natural log of 1. Since they're positive, I'm not going to worry about that. But that's 0. What's the natural log of 5? ln of 5. So we got, so here's our actual, right? And it's not going to be very good, by the way, because my delta x is 1. Okay, so it's going to be terrible. The closer your delta x's are, again, the more computation you're going to be dealing with. But you know, the more tedious it's going to be. So if you had a spreadsheet available to you, I would definitely do something where I would just let you guys do this in a spreadsheet rather than showing it to me. But you know, you're going to have to program this eventually. When you take your numerical methods class, you're going to be programming this. So this is my actual minus experimental, right? That's the trial that we did, right? That's the 101/60. So actual minus experimental divided by actual. We'll go ahead and make the absolute value there times 100. So I don't know how much lab experience, how many lab classes you've had at this point. If you haven't had any, this is your percent error, right? It's actual or calculated minus the experimental. That's the numerical thing that we just did, divided by the actual times 100. Okay, that's your percent error. Okay, that's what that is. You will the more science classes, the more lab classes you take, the more you're probably going to be using this formula. Okay. So let's go ahead and figure out, like, how far off are we? Right. So this is 1.609. Oops. Okay. And there's a problem here because how many decimal places did I keep? So that's part. It's going to affect your value here. Okay. Minus 1.6833. We have the same number of decimal places. Okay. Divided by 1.6094. All right. And then times 100. All right. And we have about 4.6% error here. So if I pick more decimal places, right, we'd probably get more decimal places in here to get error. I don't think it's going to change that 4 though. But clearly, right, if I maybe subdivided it and it said 1, 1.5, 2, 2.5, 3, 3.5, etc., it would have been a much better estimate. Okay, this is not a great estimate. Okay, it's not terrible, you know, but you know, I think we can do better. So why don't we take a look at Simpson's rule? So just using Simpson's rule on exactly the same kind of problem with the same values, that we can compare the errors to see how close we are in each case. They actually have you do some error calculations, some better error calculations in the book. This is what I don't like about your book on this one. Oh, how about that? I used exactly, well, not quite the same one, but close. Do we have Simpson's rule? Where are we? The Simpson's rule. Okay, sorry about that. Yeah, so the error bounds that they have here, it kind of gets me a little bit because again, you don't usually use this on functions that you know. You use this on functions that you need to have dots with. So, you know, the fact that you can take a fourth derivative, again, easier said than done. Okay, it's trapezoid rule. Where's Simpson's rule? Arrow bounds. Sorry. I bet it's the next page. There we go, Simpsons rule. Beautiful. Okay. Yeah, they go through and show you where this comes from, and we can do that tomorrow. Okay. But see, they did the same thing. They went through exactly the same thing I did. Okay. Let me give you the formula. Right, delta x over 3. Now they are a little bit different because we're adding up polynomials. We're adding up parabolas here. Okay, so it's 1, then it's 4, 2, 4, 2, 4, 2 forever. Okay, so it's f of x0 plus 4 f of x1 plus 2 f of x2 plus 4 f of x3 plus 2 f of x4 plus 4 and then 2 and then 4 and then 2 until you get to the last one where it's just f of xn. Right? You need an even number. Okay, we need an even number. So that's what we're going to have there for an even number. All right. Because this has to land right on a 2, so we can go to a 1. All right. So in this case, again, we have our x's. We have our f of x's. We have 1, 2, 3, 4, 5. We have 1, half, third, fourth, and a fifth. All right. And then we're going to calculate Simpson's rule for this. Okay. So we have 1/3, right? Because delta x in this case was 1, right? And then our first value is just going to be 1 f of x0 or x1 plus, and then we go up and we have 4 of them. Okay, so we have 4 f of x2 plus 2 f of x3. And then that's all we had, right? We just have one more. So it goes down to 1 f of x4. Okay? So you have to have an even number because this 2-1 sequence has to happen. Right? So we have 4, 2, 4, 2, 4, 2, 4, 2, and then back down to 1. Okay. So that's something to remember about that. That's the limitation of Simpson's rule, is that you have to have an even number of things. A lot of time that is your choice. So, you know, if you want an even number, then you have that in your power to decide, like, well, I'm going to let my delta x equal whatever, so that I'm going to have an even number of subdivisions. Okay. The books right now, where we are with doing it, they're going to tell you what your delta x is, or they're going to tell you what your b minus a over n. You can just choose whatever your n is to make sure that it's even, right? So if I wanted to say, oh, 5 minus, and I wanted an even number, I could say 10, right? And then we could say delta x is equal to 2/5, and then it would say, right, instead of this, we could say 1 and 2/5, 1 and 4/5. It'll be 1 and 6/5, but that's really 2 and a 5th, and then go up that way. Okay, so it is, you know, outside of calculus textbook times, this is largely up to you. And actually, it's going to be largely like, what error do you want to tolerate? We'll talk about that a little bit tomorrow too. Okay, so yeah, here we go. We have 1/3, and again we have 1 times 1, 4 times a half, 2 times a third. We have 1, 4, 2, and then 1 times a fourth. I think that's what we're going to do here. we have first, we have 1, 2, 4, 2, 1. 1, 4, 2. Oh, maybe I was wrong with that. Oh, sorry. The 4 has to be the end. I was mistaken. Okay. I am mistaken on that one. Because this is not turning out right. I should have everybody. 4, and then finally 1. All right, so there we go. So let's go ahead and add this up. So this is going to be 1/3, and then we're going to have 1 plus 2 plus 2/3 plus 1 plus 1/5. All right. So let's go ahead and add that. So we're going to have 1/3 times parentheses, and I've got 1 plus 2 plus 2/3 plus 1 plus 1/5. All right. And we'll go ahead and convert that to a fraction just for the moment. Okay. 73/45. I really shouldn't have bothered converting it to a fraction, right? Because what we're going to do next is we're going to take our natural log of, right, that was natural log 5. ln 5. And we're going to say, right, actual minus experimental divided by actual times 100, right, to get a relative error. So we'll say this is 1.6094 minus, and this one was pretty easy. This was 1.6222. Okay, divided by 1.6094 times 100, and we'll go with that. So 1.6094 minus 1.6222, and then divided by 1.6094, and then times 100. Okay, so absolute value. So this was about 0.8% error, okay, which is a lot better than 4.6% error. Okay, I'd rather put up with this than put up with this one. So, like I said, at one time, without calculators, trapezoidal was probably a more convenient way of doing things, but you know, you have to suffer more error with it. Simpsons rule, I think it almost, I can't think of a case where Simpsons rule does not give you a better result than trapezoid rule. So this is the one I just always use because it's a lot easier. But you know, there will definitely be times, mostly in the instructions, where they're going to tell you to use the trapezoid rule, so you get a chance to use them both. Okay, but you know, professionally, that's probably the way you're going to go with Simpsons rule. Okay. All right. I think I should probably stop talking now and call it a day. We can do a little bit more with error tomorrow and how to get like how many subdivisions to get in order to make the error that you want. Okay, because you are going to, you know, there's always going to be error with this stuff. The only time there isn't, if you ever become a math teacher, don't have them do Simpsons rule on a parabola, because you will get 0 error. Okay, because Simpsons rule approximates a parabola to get the area underneath of a parabola. So don't do it to a parabola. But every complicated function, you're going to you know, you're going to have some error with it. Okay, so I'll stop and I will see you tomorrow. Okay, very good.